Hello everybody. In this lecture I will be discussing with you about full wave rectifier. As we have already come across the half wave rectifier in the previous class, and now you know what it is and how it is constructed and how it operates. In a full wave rectifier, instead of one single diode that was used for a half wave rectifier, we need two rectifiers at least. Now this full wave rectifier is basically of two types. One is center tapped and another is bridge, based on the configuration. Now for center tapped rectifier, center tapped full wave rectifier, we need two diodes, and for bridge rectifier we need 4 diodes. So first let us discuss about the center tapped rectifier configuration. If you look at the simple circuit of center tapped rectifier, it will be something like this. Here we are selecting two diodes, one is this one, another is this one. This is my load resistance RL, D1 and D2 are the two diodes. The AC mains, the input supply is applied over here, and during a particular instant this side is positive and this side is negative, and at the other instant this side will be negative and this side will be positive. Accordingly, if this is a step down transformer, voltage will be step down from the primary side to the secondary side, and an input sinusoidal signal like this has been applied at the input side. So now this is a normal circuit. The primary side is having number of turns N1 and the secondary side is having number of turns N2. So it is N1 is to N2 transformer, step down transformer, and basically the center tapping is done at the secondary side. It is something like this, how it is connected. The secondary is segregated at its midpoint, and from there a connection is made to ground. Now this is the actual center tapped configuration of a full wave rectifier. Center tapped configuration of full wave rectifier. Now this full wave rectifier is equivalent to two half wave rectifiers, obviously. So this full wave is equivalent to two half waves rectifiers, and because of the center tap at the secondary side, each of these rectifiers, or rather we can say each of these diodes, they are single-handedly can handle the signal that is being obtained from the secondary side, but because of the center tapped, the actual secondary voltage is divided by 2. So the input that is being obtained at each of these diodes is half of the total secondary voltage. And if we now consider the waveforms of operation, so let us see how it looks like. Suppose this is the input signal waveform. This is V in. And continuing with that, let us first see what happens during the positive half cycle, how this circuit will look like. During the positive half cycle, the circuit will look like this. This side is plus and this side is minus, and accordingly the primary side of the transformer will have this side plus and this side minus. Obviously the secondary side will be having this side as plus and this side as minus. And this is grounded. The diode is connected over here. That is connected to the load resistance, which is grounded. So this is the equivalent circuit during the positive half cycle. This part of the input signal, and in this case you can see, because of plus here, that is connected to the P side or anode of the diode, that means this diode is forward biased and it will conduct, and it will act like a closed switch. So whatever will be there as the secondary voltage will be replicated at the output of this load resistance RL. So if we consider VO as the output voltage, so VO will be a replica of secondary voltage Vs. If this is Vs, we consider it is a replica of secondary voltage Vs. Now this Vs will be obviously, if this is the total Vs, if this is the total Vs, then this Vs, rather we should write it as Vs prime. This Vs prime will be obviously Vs divided by 2, and this is happening because of center tapping. Because of center tapping. The same thing will be conceptualized for the negative half cycle operation. So the diode will conduct and the output voltage will be replicated as per the input voltage. So now, what should be the waveform? How it should look like? Let us see. The waveform should look like, the positive part will be replicated. So we should be getting this one, we should be getting this one because of this positive half cycle, we should be getting another one because of this third positive half cycle, and so on. So if we now consider the negative half cycle, here also similarly the center tapping formula, that is Vs prime equal to Vs, will hold. That means the actual secondary voltage will be half of the total secondary voltage, and that is the input voltage to the second diode in the negative half cycle. So the equivalent circuit in the negative half cycle should be looking like this. The diode should lie over here. This is the load resistance, which is grounded, and the other side of the secondary is also grounded. Now for this negative half cycle operation, this side is minus, this side is plus, so this side is minus and this side is plus, this side is minus and this side is plus. So as a result of this, since this side is plus connected to the anode of this diode will conduct, and at the same time, as in the previous case, the upper diode that is, this diode will be conducting in the positive half cycle and this diode will be conducting in the negative half cycle. On the contrary, this diode will be off, non-conducting in the positive half cycle, and this diode will be non-conducting in the negative half cycle. So at any point of time, based on the positive or negative cycle of operation, only one diode will conduct, and at the same time the other diode will be in non-conducting condition or switched off condition. So in this negative half cycle, how the waveform at the output will look like, let us see. This is VO at the output voltage will be replicated by the input voltage. So whatever is there at the input voltage during the negative half cycle, that will be replicated at the output. So it should be like this. This side, this is negative, this is negative. So for these two parts, we should be having this waveform and we should be having this waveform. So if we now combine the two, that is this one and this one, we should be having this common waveform, which is the load current. So this is nothing but the diode current ID1 and this is nothing but the diode current ID2. That means this is the current conducted by this diode ID1 and this is the current conducted by this diode ID2, and that is being plotted over here in these two waveforms. Now combining these two, we can write that ID1 plus ID2 is nothing but IL, where IL is the load current, and VO, output voltage, is nothing but IL into RL. So if we now plot this IL that is combining ID1 and ID2, we should be getting, just combine these two waveforms, so we will be getting a series of these half cycle waves like this. So in this fashion, we can say this IL is the full wave rectified output. So this is nothing but full wave rectified output of this center tapped configuration full wave rectifier. Now the question arises, why during the negative half cycle this waveform, rather going downwards at the input, why after the conduction by the diode it is swinging upward? That means the polarity, why its polarity is reversed than from the original input, that is this one. This is because you can understand that the direction of current when the diode is conducting either in positive half cycle or in negative half cycle, in both the cases the direction of current that is being flown through the RL is from this top to bottom. Here also it is going like this and it is going from top to bottom. That means the voltage polarity at the output of the load resistance RL is always same for both the half cycle of operation. So that's why we can say that during both the half cycles of operation, the direction of current flow through the load resistance is same, and as a result the polarity of voltage drop across the load resistance, that is VO, that is being measured by a voltmeter, is always same, and the magnitude will also be same at the corresponding instants. So we can say that this is a unidirectional movement of current through the load resistance, and that's why we can say this is nothing but a pulsating DC. Because of unidirectional movement of current across the load resistance after the current conduction is done by both the diodes at both the half cycles, this unidirectionality proves that it is giving us a DC, but in the form of pulsating DC. So in this way we can say that the full wave rectifier will give a conversion from AC at the input into a pulsating DC at its output. So in conclusion, we can say that a full wave rectifier output is twice that of a half wave rectifier, and a full wave rectifier acts as the same as like two back-to-back connected half wave rectifiers. That means if we connect back-to-back two half wave rectifiers, whatever output it will be giving us, that should be equivalent to the output from a full wave rectifier. Now if we incorporate second approximation cases to the ideal diodes, that is the if they are used in this rectification purpose of full wave rectifier, then we should say that this Vs prime, that is the input of the individual diodes during the individual half cycles of operation, will be changed to a value Vs prime minus 0.7 if they are silicon diodes. So this will be, suppose Vs double prime. So Vs double prime will be the actual input voltage required for the diodes to conduct. That means incorporating the second approximation in this case. So we can say that after the at its input of each diode in that is comprising the full wave rectifier, if you apply Vs prime as its input voltage, only then the diode will conduct. So this is all about the full wave rectifier in center tap configuration. Now let us see the next type of full wave rectifier, that is bridge type. Bridge type full wave rectifier. Now let us consider first the bridge type rectifier circuit. A bridge rectifier is similar to a full wave rectifier because it produces a full wave output, as just we have seen. But in this case, I have already told you 4 diodes are required, and the idea is 2 of them will conduct at a time, and at that time the other 2 will not conduct. So in bridge rectifier, diodes will conduct or non-conduct in pairs at each individual half cycles. So as a result, the rectified load current flows during both the half cycles and a full wave rectified output is obtained. Now let us see the full wave connection of the circuit. This is the load resistance RL connected to ground, and this side, the other side, the opposite side of the load resistance, that is also connected to ground, and the other 2 parts of the secondary is connected to the opposite nodes of the bridge. So this is how the bridge type rectifier, full wave rectifier, is configured or constructed. So this side is the primary voltage Vp, and this side will be the secondary voltage Vs, the whole. Here once again it is N1 is to N2 step down transformer, But in this case the difference with a center tap rectifier is the as in the previous case we have just seen that Vs prime is actually Vs by 2. The actual input to the diodes will be half of the overall secondary voltage, but in this case the whole secondary voltage is being applied across the bridge, as because there is no presence of center tapping. The diodes are numbered as, this is D1, this is D2, D4, and this is D3. So this is the operation, this is the construction. So let us see what happens during positive half cycle, how the circuit will work, what is the equivalent circuit. The equivalent circuit will look like this. Since this is positive half cycle, so this is plus, this is minus, this is plus, this is minus. Now during the positive half cycle you can see from here, since this side is plus, so this side is plus, so this plus is connected to, the current is flowing in this direction, that means this plus is connected to this one, anode of D1 and cathode of D3. That means it is making D1 forward biased but D3 reverse biased. So this side is plus and this side is minus. So during the positive half cycle, this plus is connected with the anode of D1 but cathode of D3, and similarly it is once again connected through this with this, if I consider this minus, this is minus, so this side is open and this side is closed. That means D1 will conduct during the positive half cycle, D3 will be off, so no current will be gone through this branch. So the current will flow through this through to this D1, and that will flow inside this through this path, and that it will go across the resistance load resistance RL into ground. Then minus at this side, so this side of the secondary with minus, that is being connected with the negative, that means the cathode terminal of D2, that means it is making D2 forward biased, and anode terminal of D4 and making D4 as reverse bias. So in this case D4 is off and D2 is on, that means D2 will conduct. So at the same time, when so the current in the negative half cycle will flow in through D2 via this current in the positive half cycle will flow via D1 and D2 but not via D3 and D4, and the circuit is like this. It will, the current path will be like this. It will flow through this in this fashion. It will go into this, into the ground, and that ground is connected over here. The current will enter once again through this. It will go through this D2 and it will take the path of the transformer towards the transformer secondary, and it will come over here. So in this way the circuit is closed, the current conduction path is closed. So this is during the positive half cycle. So we can draw the circuit like this. So this is RL. So what we are seeing, that D1 and D2 is closed like this. D1 and D2 is conducting. This is D1 and this is D2. D1 and D2 is conducting current through load resistance RL, but D3 and D4 is not shown. That means they are non-conducting. So this is the equivalent circuit in the positive half cycle for this bridge rectifier, and as a result of this the output will be something like this one. if the input signal is this type. That means at the primary of the rectifier. This will be the output across the load resistance RL for conduction by the D1 and D2. Let us now consider the conduction for the other direction. In the other direction, obviously, then D1 and D2 will be non-conducting and D3 and D4 will be conducting. And the direction of current will be, this side will be minus, here this side will be minus and this side will be plus. So this plus is connected with the cathode of D2 making it non-conducting and anode of D4 making it conducting. So this side is plus, will make the current to flow from the lower side of transformer secondary through this path. This side is open, so the current will take in this route and it will go towards this. And now once again this side is off, so the current will go through the RL into the ground in this direction, and this ground once again is connected to this ground because it is same in the same circuit, and this current will enter the bridge once again through this ground. Now this side is open, so obviously the current will go to D3. And why it will go to D3? Because D3 will conduct. And why it will conduct? Because here in this case this side is negative and this negative is connected to, in the negative half cycle, this negative is connected to the cathode of this making this forward biased and to the anode of this making this reverse biased. So this side is open, so this D3 will be conducting and as D4 will be conducting. So the direction of current will go through this area and this side is off, so this will go take its turn towards this, and it will complete its journey at the other part of the transformer secondary. So how the circuit will look like in the negative half cycle, the equivalent circuit. This is the current conduction path. I have drawn in the black color. So the current conduction path you have just seen. So the circuit will look like this. This side is minus, this side is plus. This is the primary, so this is minus, this is plus, and the secondary side will also, this side is minus, this side is plus. This side is grounded, this is D3, and the other side will go inside the other diode. This is D4, and it is connected to load resistance RL. So the output, how it will look like? It will look like the other one. So the output will look like this one. In the previous case, it was during the positive half cycle, the output will look like this one. In the negative half cycle, the output will look like this one. So if we now combine the two, once again, like the similar one, the output VO or load current will be the combination of the two cycles of operation, positive and negative. That means it is a series of all half waves. So this is nothing but the pulsating DC. Once again, full wave rectified output at the bridge rectifier. So the output or the replication of the output will be same, but the configuration or the construction and the way of operation of the two rectifier configurations are different, but the output is same. And if we incorporate the second approximation in this case, since we are using two diodes are at a time operating, so 0.7 for each diode into 2, that means 1.4 volt is the actual amount of voltage that is being used, that is being required as the barrier potential for the two diodes to conduct at the same time. So this much amount of voltage will be subtracted from the transformer secondary, that is you have to do for mathematical calculations, Vs minus, if Vs is the secondary voltage, Vs minus 1.4. This will be the effective input voltage for the two diodes to conduct in a bridge type configuration. So we can say that bridge rectifier also acts like two back-to-back half wave rectifiers. And also you have to note that during both the half cycles, the load voltage has the same polarity and the load current flows in the same direction. So that's why we can say the output is a DC and in the pulsating form. And the advantage of this, one of the biggest advantage of this bridge type of full wave rectification over the center tapped version is the entire secondary voltage that can be used in this case, where in the previous case only the half of the secondary voltage is used. Another advantage we can say in this case, the size for the same DC output voltage, the size of the transformer in the bridge rectifier is much smaller than the center tapped rectifier. Each diode, another advantage is each diode has only the transformer secondary voltage across it in the reverse cycle. So the required PIV rating, I will come into that in a little while later, is nearly equal to the peak voltage of the transformer secondary, and only half of that required of a full wave rectifier, because in that case no center tapping is done. No center tapping is done in case of a bridge rectifier. So the PIV rating requirement for the operation by the diodes will be half of that required for a center tapped configuration. There are some disadvantages also. Bridge rectifier requires 4 rectifying elements, whereas in center tapped you have seen it is only 2. And another thing, during each half cycle the current flows through 2 diodes connected in series, causing a large power loss in case of a bridge configuration than in case of a center tapped configuration. And for this reason this bridge type circuit is rarely used for low voltage rectification, because if more number of diodes or devices being used, their internal potential drops will hamper the overall circuit operation. So since here we are using 4 number of diodes as compared to the 2 numbers in case of center tap, so in case of bridge rectifier the power loss or the potential loss, chances of potential loss is more. So for low voltage applications the bridge rectifiers are not preferred. So this is all about the full wave rectification concepts, and also the different configurations of center tapped and bridge rectification. In the next class I will be discussing with you about the use of filters at the output of the rectifiers, and also the different factors or the parameters giving the quality of rectification. That means we will be analyzing about the quality of rectification in terms of different parameters or factors. Thank you.